So welcome back, everyone. So now it's time to actually run some simulations. So in this talk, I'm going to be walking you through the basics of how to actually run some simulations with OpenMM, and then you will do some exercises of actually doing it yourselves. Hopefully everyone's now got some sort of computer that you can reasonably run these on. So I actually find it a little difficult to explain exactly what OpenMM is. Take this as a pop quiz. I hope you all studied for it. What is OpenMM? Is it A, an application for running molecular simulations? Or is it B, a library of simulation routines for applications to use? Or is it C, a domain-specific language for molecular simulation? Or D, is it all of the above? Anyone want to answer? Did I hear a D out there? We've got a genius in the audience. Excellent. Yes, it is all of the above. For the most part, in this workshop, we're going to be focusing on A, on just how to use it as an application for running molecular simulations. Tomorrow, though, we will get into some of the other ways that you can use it and the very powerful features that OpenMM offers. So what is OpenMM? So it really is two main pieces. There is a low-level computational library. It's written in C++. And this library just implements lots and lots of different calculations that come up in running molecular simulations. So evaluating forces and energies, doing numerical integration, applying constraints, doing minimizations, that sort of thing. And then we have, on top of that, a high-level application layer that's written in Python. And that layer adds many features that you need for an actual MD application, things like loading and saving common file formats, things like writing out results in the middle of a simulation, or building a description of a molecule based on a force field. OpenMM is written to run on many different types of hardware, so we support both CPUs and GPUs, and we support ones from many different vendors, so NVIDIA, AMD, Intel. We support the most recent GPUs from all of these vendors, which is one of the ways that OpenMM is really unique. It's designed to address various types of needs for various different types of users. So we sort of distinguish between three main categories of users. So first, there are biologists and chemists. These are people who are interested in studying biology or chemistry. They want to run simulations of molecules and learn things about the nature of these molecules. And so these people would be mainly focused on using the application layer to run simulations. Another important group of users is application developers. These are people who are programmers who are writing their own applications, but they want to include simulation features in their applications. And so instead of having to implement all these many, many different sorts of calculations themselves, they can just use the OpenMM library in order to perform these calculations for them. A third class of people is algorithm developers. These are largely going to be, possibly chemists, possibly computer scientists, possibly mathematicians or statisticians, but people who are trying to come up with new methodologies for running MD simulations, new approaches to simulations. And so these people can use a mix of both the Python and C++ layers, and also some features that we have like custom forces and custom integrators that I'll tell you a bit about tomorrow, which allow them very easily to implement completely new algorithms. And this makes OpenMM an incredibly powerful tool for these people who are trying to very easily create completely new MD techniques. So, how do you actually run a simulation in OpenMM? So I need to first explain that what I'm calling the application layer isn't exactly an application. Really, it's a set of Python libraries. And so what happens is that you write your own application. You write a Python script that calls these libraries, and that script is your MD application. Now, I should ask, how many of you are experienced Python programmers? Raise your hand if you are. I'm seeing a lot of people not raising your hands. And so the rest of you are probably thinking, oh my God, what am I doing here? Is that correct? Don't worry. No programming experience is required to do this. And here's how I like to think about this. Any MD application is going to require you to write some sort of a script to tell it what calculations you want to do. And different MD applications use different approaches to writing the script. but they all have some sort of a script. And in the case of OpenMM, that script happens to be written in Python. But that doesn't make it any harder to write than any of the others. In fact, well, I'm a programmer, and I'd say it's much easier to write than these long lists of magic symbols that you have to do in some other MD applications. So it's really easy to do, and we'll walk you through the whole process. So here is an example of a complete script, a complete molecular dynamics application written in OpenMM. This whole thing is 12 lines of code, and this does a lot. And I'm going to walk you through this whole script now and show you line by line exactly what it's doing, and you'll see how easy it would be to take the script and modify it to do whatever you need it to do. So the first thing it does is these a few lines that say from blank import star. You don't even need to worry about these. These are just telling Python that we're going to be using the OpenMM libraries. These lines go at the top of the script. Don't worry about the details of them. So the next thing we do is we're going to load in a PDB file. So in this case, it's a file called input.pdb. Of course, you can give it any file name you want there. Technically, what we're doing here is we are constructing a PDB file object and passing this string, input.pdb, to the constructor, and then we assign it to a variable called pdb. The details don't really matter much, just this line is telling it, load this file. All right, so we've loaded a PDB file. Next, we need to select what force field we want to use to simulate this protein. There are, of course, many different force fields out there. You've heard a little bit about that in the earlier talks. OpenMM comes with a bunch of force fields built in, many of the most popular ones. Though it's not limited to those, it is totally possible to create new force fields that work with OpenMM. So here what we do is we create a force field object and assign it to a variable called force field. But here we're just passing in the names of two files that it should load. Amber99SB is the main force field that we're going to use. This is a widely used force field. And we separately tell it what water model we want to use. And so we're going to say use the tip3p water model. So having got our PDB file and having got our force field, we now say, OK, use that force field to model that protein. And we do this by calling forcefield.createSystem. This is, technically speaking, a method that we call in the force field object, and it creates a system object that we assign to a variable called system. But the really important thing about this line is we get to specify a whole lot of options here about how we want to model our system. So we are telling it here that we want to use the particle mesh AWALT, PME method, for representing long-range interactions. There are a number of other options we could have specified instead. We're saying that we want to cut off the non-bonded interactions with a cutoff distance of 1 nanometer. Because we're using PME, this doesn't actually mean there is no interaction beyond that. It just means that we use a different mathematical technique to handle the longer-range interactions. We say constraints equals H bonds, which means constrain the length of any bond that involves a hydrogen. So keep the length of those rigid. The advantage of doing that is that those are the very fastest motions in the system. And so if we make those rigid, it allows us to use twice as large a time step, and we can simulate more. And there are many other options that you could have specified here. And there's a whole section in the manual that goes in great detail through all these different options that you could specify. OK, so we've set up the system that we want to simulate. Now we need to select an integration method that we want to use. And in an earlier talk, you heard about different types of integration methods. And so we're saying we're going to use a Langevin integrator. This is one of the ones that Liping talked about. And we give it a few options. So we're saying we want to use a heat bath that is set at 300 Kelvin. So that will be the temperature of our simulation. And we want to couple the protein to this heat bath using a friction constant of 1 inverse picosecond, and we're going to use a time step of 0.002 picoseconds, or 2 femtoseconds. So we've set up all our options. Now we're ready to actually begin a simulation, to run something. And the way we do this is to create a simulation object, and we pass it the information that we've loaded from all these earlier things. And this is when it actually says, OK, let's allocate memory for all these things. Let's go and get everything set up on the GPU. Now we're all ready to run a simulation. First thing we need to do, though, is to tell it, oh, by the way, we loaded a bunch of atomic positions coordinates from the PDB file. So let's set our simulation. These are the atomic positions we want to start from. Now, we could just run our simulation here, but usually that's not a good idea. And the reason is that who knows where those coordinates came from. Maybe they came from a crystallography experiment. If so, it's probably, those coordinates may have a lot of uncertainty in them. They probably aren't at any sort of local minimum of whatever force field you're using. And so if we just started there, we'd probably have huge forces and your system would blow up instantly. So instead what we do is we call simulation.minimizeEnergy. And this just tells it, run a local energy minimization, just wiggle around those atomic coordinates a little bit so that you get something that doesn't have any huge forces, so our simulation won't immediately blow up. Now, we could just run a simulation, but that's not very interesting if we don't get any data out of our simulation. So we're going to say we're going to attach a reporter to our simulation. A reporter is something that outputs information as the simulation runs. And this particular one we're going to add is a PDB reporter. You could probably guess what that does. It outputs PDB files, or just one PDB file, and adds frames to it. We're saying that the name of our PDB file will be output.pdb. I know it's a really clever name. And it should save a frame every 1,000 time steps. And having done that, we now say simulation.step. We tell it take 10,000 steps, and it runs, and it takes 10,000 steps, and it saves every 1,000 step to our PDB file. So there we have a complete script for running an MD simulation. How do you actually run it? Well, there's a couple of ways you can do it. One way would be to take this script, save it to a file on your computer called like simulatepdb.py, and then you would just run it from the command line. You would type python space simulatepdb.py. Another way you can do it is by using IPython Notebook. And this is what we're going to do with all the examples in this workshop. IPython Notebook is a really nice interface for running Python scripts. It's a program. It runs on your computer, but it displays its user interface through a web browser. So to launch it, all you do is just bring up a command line and go to your CD to the directory containing all your examples, and you just type IPython space notebook, all lowercase, not the way it's written here. So your turn to try to do this. So hopefully you've all got things set up so you can try to run this. And so just bring up a command window, CD to the examples directory, and type IPython space notebook. And hopefully that will get you there and you can all run the simulation.